12.2c, we're going to use transformations involving logarithms to achieve linearity for a relationship between two variables. So remember one thing about linearity. This is the standard format of the line. And this right here is the format of actually what a exponential function would look like. So an exponential function, unlike a power function, remember the power functions, this is what we changed. It was either squared, cubed, or the fourth. This is an exponential. Exponentials, their inverse functions are actually logarithms. So now we're kind of switching from looking at quadratics and cubics, and we're looking at exponentials and logs. So in this case, it's good to recall this pattern here is growth is exponential and that's decay. All that happens is the b value changes or the base. So just kind of a nice recollection. Now we can take any exponential and we can create a logarithm. So you don't necessarily have to remember this, but maybe you do. What you can do is remember if this is exponential base 10, it's actually going to be log base 10. So I can convert it. I could do log base 10 of x equals y, kind of doing this swoosh thing. So if I convert an exponential, I can actually get this corresponding log. So how do you linearize relationships that follow an exponential or a logarithmic pattern, basically? Well, if I do, what you would first do in this case is you would come on in and you would take the log of both sides. Remember in Algebra 2 and in pre-calc, you learned if you had a function like this, you could take the log of both sides. That's fair. Well, if we do that, we can use property of logarithms and pull this apart through addition. So log of a plus the log of b to the x. But then also recall, we said exponents in log world can be brought forward. So technically, it can be transformed like this. Now, again, you don't necessarily have to understand this, but this is what you need to take away from it. If you want to linearize exponential functions, what you must do is just take the log of y. Why do I make that conclusion? Because if you look at this format, the y has the log. The x has no log in front of it. So if you have an exponential pattern in your data, which either looks like growth or decay, all you do is take the log of y, and what that will do is actually take the curve and make it linear. Let's look at this carbon dating question. When scientists estimate the age of fossils, they often measure the amount of radioactivity isotope carbon-14 that remains. Carbon-14 has a half-life of approximately 5,730 years, meaning that in 5,730 years, the amount of carbon-14 will be half of what originally was. Suppose the organic matter in a fossil originally had 1,000 milligrams. After this many years, the carbon-14 should be at 500. Find the amount of carbon-14 remaining after X years using this particular function. Here's the graph, by the way. This is a great pattern of exponential decay. Now, if we wanted to linearize this, because it looks like exponential decay, I could see a multiple choice question. They'd ask you what to do. You guys, all you have to say is this. To linearize it, you would take the log of y. So what you would do, you would keep the x as years. You would now take all of these and do the logs of the carbon-14. You would graph the new data and it would become linear. Ultimately, your new scatter plot, if you did it, again, you would keep the years as this, and you would take the log of all those answers of how much carbon-14 was in there, and surprisingly enough, again, you're going to see that linear pattern. Talk about the M&Ms we did back in chapter 11. Suppose a student opened a bag of M&Ms, dumped them out, and ate the ones with the M on top. When he finished, he put the remaining 30 M&Ms back in the bag and repeated the same process over and over until all the M&Ms were gone. Here's a table of a scatter plot showing the relationship between the end of each course. So after end of each course, he flipped out the M&Ms. If the M was showing, he ate them. Here's how many there were left. If you sketch this, you're going to see it looks like an exponential decay function. So it's an exponential type of pattern. And that's really what you want to recognize. It looks like they're being cut in half. So to linearize anything exponential, again, all I'm going to do is take the log of the y values. So here's what they did. A scatter plot of the natural log. So they used the natural log instead. What they did, again, is they kept the course here as our x value. So this was the x. Our y's then, they just took the natural log of all of these values, so natural log of 30, natural log of 13, and they recorded what they were. They then just graphed this as x and y, and here's what happened to that data. Be careful, the last observation is not included since the natural log of y is undefined. Explain why it would be reasonable to use an exponential model to describe the linear relationship between m&ms in this course. Well, first of all, if there is an exponential relationship between two variables x and y, we expect the new scatter plot to be x natural log of y. By the way, they could have used log base 10 or log base 3, just using natural log. That should actually be roughly linear. Well, it was. So since the scatter plot of the natural log of the remaining m&ms versus the course number is roughly linear, an exponential model definitely seems appropriate here. Continuing with the m&ms, here's the Minitab output from the linear regression analysis on that transformed data. So remember, the transformed data was just x natural log of y, so I don't forget it. They want us to write the equation for the least squares regression line. Now here's where you just have to be careful. This data was transformed. Data here doesn't just represent x and then our y-intercept. This actually now represents the natural log of our y value. So to write the equation, what you would write is this. It ends up being, remember in our transformation, we had that x and natural log of y. So x stays the same, but you have to write the natural log of y hat. You're still going to use the constant and the slope that's stated. None of that is any different. Same process. Now, I do want to define the variables, though. So I'm going to say, let the natural log of y hat be the predicted value of natural log number of m&ms remaining, and x is still the course number. Fine, let's go to 12.2d. Make a prediction using this model. Okay, use your model to predict the original number of m&ms in the bag. Well, the original number would be before the courses start, so let's do that when x equals 0 to make a prediction. So I'm going to take my particular equation, put 0 in for x. So when I do that, I'm going to actually get this value right here. What you should notice, a 0 times the slope is just 0, so all I'm really left with is this value right here. Now, how do you convert and get the y out of there to solve for it? Well, if you're not sure and it's multiple choice, guess and check. That's fine. Look at the various choices and plug it in and see if it works. That works fine. The math behind this, if you remember though, the natural log of y equals 4.0593. Natural log is just log base e. So what you can do is you can take the base of the log, and you take the base of the log, raise it to this exponent equals y. So when you write it, it's going to be e to the power of 4.0593 equals y hat. You put e to this power in your calculator. We could predict there should be 57.93 m&ms in our original bag when we first start. I'm curious if this is even the great model or not. So part E says this. A residual plot of the linear regression is shown over here where we have the course and the residual using our transformation of the natural log of y. Discuss the appropriateness of the graph. Well, since there's no obvious leftover curvature in the residual plot, the model is appropriate for this data. Perfect. Last thing here, let's calculate a 95% confidence interval for the slope of the least squares regression line using that transformed data, folks. So when you put this in your calculator, you remember want to use x and the natural log of y for your list 1 and list 2. Assume all the conditions are met. So what I'm going to do here first is, here's the confidence interval format. I want 95% confident, so 0.975. We had, for our sample size was 30, so I'm going to do 30 minus 2 or 28. That's our critical value. If I go on in and I put this data into my calculator, I go to my actual tests and run the confidence interval for the slope, so the t-interval for the slope. We are going to end up getting that we can find the b and the standard error. It will compute our confidence interval for us at here. Therefore, what we can say is that we're 95% confident the true population slope of the natural log of remaining M&Ms and the course number will be between this range.